some. All right. Unfortunately, we do have a little bit more to do, so we're not going to get out of here just yet. So anyway, if R is not equal to 1, and R not equal to 1, we remember. So basically, R can be anything but 1. Then we have these relationships. All right. The limit as n approaches infinity of R to the nth power would be equal to 0 if R, the absolute value of R, is less than 1. All right, so an example of that would be, just write example. Let's say we have the limit as n approaches infinity of, I'll go simple, 1/2 to the nth power. All right. If I'm listing out the terms of the sequence here, just forget about the limit for now, just the terms of the sequence. I would have, I start with 1, so 1/2 to the first power, then 1/2 to the second power, which would be 1/4, 1/2 to the third power, 1/8, 1/16, and so on. Eventually, I'd get some value of n, right? In which case, I'd be looking at 1/2 to the nth power. So what this is asking me, or at least trying to tell me, is if I have some fractional value for R, if I have some large power that fraction is being raised to, that fraction is going to get smaller and smaller. I think we'll all agree that 1/4 is less than 1/2, 1/8 is less than 1/4, and so on. But it's going to get exponentially smaller and smaller. All right. So if I had n to the, I don't know, you can say something like the 7th power, which would be what, 1/128, I think. So that's going to be pretty small. It doesn't take too many values or too many terms in the sequence before you realize that this thing is approaching 0. Right? The terms of the sequence are getting smaller and smaller, eventually to the point where it becomes indistinguishable from 0. All right? That's what this idea is trying to tell us. What we're looking at here under these, or under this theorem, is representatives of something called a geometric sequence. And in very simplistic terms, the only way to get from one term to another, or one term to the next, is through multiplication. It's really kind of strange because I talk about multiplication, but consistently by multiplying by the same number. So the model tends to be something in the form of a times b to the x power, also known as an exponential function. All right. So anything that follows the model of an exponential function is known as a geometric sequence, just to make things as complicated as possible. Right? Yeah, you would think it would be called an exponential sequence, but that's not what it's called. The reason why they call it geometric is because if you add a dimension, and you just assume that they're all like-sided dimensions. So you have one side, length of 2, for example. That's in one dimension. But then throw in another side that's got the same exact length. We can now get the area of that two-dimensional figure, but we get it by multiplying those two values, 2 to the second power. If I want the third dimension, I have the 2 that make up the base of the three-dimensional figure, and then the one that gives it its height, so 2 to the third power. Right? So it forms the basis of some geometric system. And when we say geometric, we're talking about geometry-based. All right, so it could have a base of triangles or circles or something like that, but we tend to focus on squares. All right, and that's why when we talk about like distances, we don't say, I don't know, oh, we're gonna cover this distance of 450 circular units. That's just weird. We say, I'm gonna find, we got a fugitive out there, and we got to cover 120 square miles of space. Like, what is that? Square area, but it's not necessarily a square. I mean, I don't think the police are like, all right, rob the bank here. We got to cover 100 square miles. We can only use squares to do it. Damn it. So, let's see if we can fit a square around it. No, it could be over there. Alright. Okay, got it. Still okay. How about a really skinny rectangle that goes out? It does not literally have to be a square in order to be thinking in terms of square units. All right, so it's a numerical system, but that's the idea. So it is a geometric square-based system. Eventually, you do learn about circular-based systems and things like that, but cylindrical, spherical, well, that's a different story for the course. If the base of your exponential is not fractional, right? We're assuming that it can't be equal to 0. I'm sorry, it can't be equal to 1, because if the base of your exponential is equal to 1, well, I already know what the limit's going to be, because 1 to any power is 1. If I said find the limit as n approaches infinity of 1 to the nth power, like, well, it could be 1, because 1 to any power is 1, and the limit of a constant is equal to the constant itself, right? So that should be pretty self-explanatory, at least that part of it. But if the base is something bigger than 1, it's going to increase without bound. So when you think about like population, compound interest, things like that, something that increases without bound, maybe at a very slow rate, but it's definitely not going to converge on a particular dollar amount. I would not personally not invest in a bank account where they told me that my savings, the savings of whatever money I put in there, is going to converge on a particular number. No matter how long I put it in there, eventually it's going to converge on $500. I'm like, wait, so I put in $100 now, and so if I leave it there for 10 years, 15 years, or 100 years, once it hits 500, it's going to stop. Okay, well, I don't want that. All right, maybe you do. Maybe you want like a short-term CD or something like that. So if it matures after a period of, let's say, 5 years, and you know at the end of 5 years you're going to get that money, and you know to remember to withdraw your money after 5 years, then it's fine. But that's a different story altogether. And it's going to increase without bound, just not always at a fast rate, not as fast as you want it to be anyway. If the R value is negative, that's the fun one. Well, if you're memorizing stuff, it's not that fun because you just know that it means that the limit does not exist. It does not converge. All right? But let me give you a particular example. Let's say I have the limit as n approaches infinity of -2 to the n. Something relatively basic, because I know I have to stay away from ones. I mean, it said less than or equal to -1, so technically I could use a -1, but we already kind of explored that. So I want to keep it juicy. All right. So I'm going to rewrite this. Think how I want to do it in such a way that's not going to be confusing. Let me do it this way. Rewrite it within, rather than kind of skipping to the punchline. All right, so -2 can be thought of as -1 times 2. All right, if you have a product that's being raised to a power, each part of that product gets raised to that power. So I'm going to raise the -1 to the second power, and I'm also going to do the same thing with the 2. So this would be the same as -1 to the nth and 2 to the nth. Multiply. All right? The 2 to the nth is not the problem. In fact, if that's all there was, I would just say the limit is infinity. And that's the end of it. So if this -1 to the nth wasn't there, then it would just be this guy, and the result would be infinity. However, that -1 to the nth is there, and we learned previously that that's the same as saying that the sequence is alternating in sign. I could write it separately based on the limit rule. I could write it as -1 to the nth in its own limit, and then the limit as n approaches infinity. I'm going to go off here, 2 to the nth, and do it that way. But just conceptualize, because there's really nothing more to write. This would be an infinite result. But before you get to that, you would be bouncing back and forth between positive and negative numbers. All right? So then the question would be, well, all right, once I get to the really large numbers, is it going to be a really large negative number or a really large positive number? Because any time I take another step in the sequence, it's going to bounce from positive to negative or negative to positive. So it creates uncertainty. Anytime you have uncertainty in a limit, it means that the limit does not exist. All right? That's the misconception with limits, because people in the past have thought that if it's infinity, well, isn't infinity by definition the fact that there is no limit to the situation, right? Because if it's infinite, then there is no limit, so therefore the limit does not exist. What does not exist means that you are incapable of finding the limit. So it's more like a sine function. If you were to go out to infinity, all right, well, what part of the sine function am I going to be at once I get to that magical place called infinity? Well, fun fact, there is no place called infinity, because infinity by definition is motion. All right? So when they talk about the idea that infinity is telling us that numbers never end, well, yeah, it's great, but infinity is on the move. So every step I take towards infinity, infinity takes a step away from me. All right? So there is no destination. All right? So I can say, all right, well, infinity is at 100 million pi. And then somebody comes back and says 100,000,001 pi. So I got a positive one, you got a negative one, somebody's got something in between. We have a whole lot of uncertainty when dealing with a sine function. That's the same idea with an alternating series or sequence, unless this is going down to 0. If I can get it to the point where this limit is converging on 0, meaning that I'm looking at an R value that's less than 1, then I'm in good shape. Because whether that R value within my exponential, whether this is a positive 1/2 or a negative 1/2, it does not make a difference. Because the component of it that is positive will be converging on 0. Once that goes to 0, it doesn't matter what this is, because 0 times anything is 0. All right, so this will pull that to 0 along with it. All right, so that's the big takeaway here, because you see, I mean, look at these expressions here. Look at that one. Inverse tangent with an exponential function? That looks nightmarish. You would think. You would think. So, some of them are a little easier to see than others, but sometimes just getting a sense of what the sequence bears out is enough to tell you what's going on. All right? So, and obviously a lot of crunchy situations here. Like, for example, I mean, that one's nasty, but some of them you can look at and say, well, this one's not bad, because this is pretty much what we're talking about. What, number 9? No, I don't think so. This one converges to 0 because it takes the form of a geometric sequence. So let's talk about that one next. geometric sequence where the R value is less than 1. Right? And that would be this guy here. So it's converging to nothing. It's going to infinity. Right? That's this guy here. Ay, ay, ay. Goes to infinity. So we say it diverges. And that would be because, of course, R is greater than 1. I was merely seeing if you were all paying attention. All right, so then, you know, that one follows a particular rule. Sometimes you have to list out a few terms in the sequence in order to get a sense of what's going on. Maybe you want to do that with number 7. So a sub 1 would be radical 2. A sub 2 would be radical 2. A sub 3 would be, you guessed it, radical 2. There's no n in there, which means no matter what term of the sequence I'm looking at, it's radical 2. So a sub n, the nth term of the sequence, fun fact, they were kind of trying to tell us that from the beginning, is radical 2. So this one's kind of a gift in disguise. This converges to radical 2. And the fact of the matter is, it was already converged. It was already there. It's a horizontal line at radical 2. Doesn't matter how far out you go, it's still going to be at radical 2. All right. Let's see. Another one that I can, because I want you to be able to play around with some of these on your own. I'm looking at you. Maybe one or two that we'll do on the calculator. Number 5? Oh, I wanted you guys to do that. Okay, that's fine. So let's take a look. E to the negative 3n to the 5th power. Well, won't be too bad, at least for the first calculation. And then after that, all hell breaks loose. So e to the negative 3rd, okay, that part is all right. And the inverse tangent, radical 7 over negative 8. So negative radical 7 over 8.
Inverse?
Oh, inverse. Okay. All right. So let's see what the next one is looking like. So 2 to the 5th power is 32. So negative 96. Inverse tangent. Plug in a 2. We're looking at rad 14 over negative 5. So negative rad 14 over 5. Okay, so I think we have it. I'm going to do one more to play it safe. I don't think he knows the password. All right, so like I said, maybe one more to play it safe. And that's, I mean, that's a loose definition of safe, because, I mean, it's pretty gross. So can't do 3 because we get undefined, right? Well, we'll get to that in a second. So let's focus on the E part of it. No, E.
Zero.
Why are we doing it if we know it's gonna break?
Is it going to break?
Yeah.
Zero
The
is
tangent
not
doesn't work because you're dividing by zero inside the intersection. So like, it doesn't matter what we do.
So once I get past 3,
Once we pass it, now you already solved it in three. It's broken.
because I want to look at E. I really, really do. So if I plug in a 3 for n, I'm going to get negative 3 times 3 to the 6th power, or 3 to the 5th power. All right? So that's the same as saying negative 3 to the 6th power. And then we have the undefined component of it. So I'll just write 1 over 0. It doesn't matter what it is. All right? But what we have from this is the idea that, okay, so the tangent part failed for this component, but it's going to pass for pretty much everything else, because the only other value that we can undefine would be negative 3, and that's not in the domain, any domain. So just focusing on the E. A negative exponent puts E in the denominator. All right? So I could even ignore the 4 if I want, but I'm not going to. So so E, instead of writing this as negative 3, e to the negative 3, n to the 5th, I can rewrite that as 1 over e to the 3, n to the 5th. All right? So I can write this as 1 over e to the 3 times 4 to the 5th power. And then I can take care of my inverse tangent stuff. All right, and it actually doesn't even matter at this point what it's going to be within the tangent. So, but if I put it in, it's what, rad 28 over 7. All right. And all an inverse tangent is asking us to do is find the angle that goes along with the ratio. So tangent ratios are infinite. So they don't exist at particular angular measures, but we're not asked to find angles. We're not asked to input angles. We're asked to input real numbers. So we're good in that regard. The idea being that we'll get some number for the tangent component. Doesn't matter what it is. Because 1 over e to the 3 n to the 5th is going to what? It's going to 0. All right, so as this gets larger and larger, this part is getting smaller and smaller and converging on 0. As long as this stays real, this whole thing is going to 0. It's going to converge to 0. All right. But it kind of, I don't know if it required it, but you did need to kind of sink your teeth into it a little bit in order to get a sense of what's going on. And so sometimes listening out, going back to like, why the first 4 terms of the sequence? Well, personally, I tend to notice the pattern after the first 3 or 4 terms of the sequence, usually the 4th. Because what I do is I notice the pattern after the 3rd term, and I test it out by figuring out the 4th term, and then I go from there. So it's almost always, for me anyway, the 4th term before I really, hypothesis, put the hypothesis to the test, and then at that point I can draw my conclusions. So it's almost, for me, always the 4th term. Although I did it like this for fun, just to prove a point, because we kind of knew it from there. All right. So what you're going to want to do is take some time and tackle some of these problems. Some of them are easier than others. Some take a little getting used to. The calculator is a good resource. Take a look at the graph. Oftentimes the graph, just look for a horizontal asymptote. Oftentimes the graph is all you need. All right, I stayed away from a graphical approach because the data mining part of this is pretty important.